Yeah, Susanna's going to tell us all about Marlow Energy Group.
Welcome to everybody who's new to Marlow Energy Group. It's great to have you, and thank you for dialing in tonight. We do these efforts almost monthly, so please keep an eye out for further ones. I'll tell you a little bit about the Energy Group, which was incorporated about a year ago as a not-for-profit community benefit society. We have a few goals and ambitions, which are first off to make Marlow a net zero carbon town, to facilitate knowledge exchange, effective networking and collaboration, and to develop and invest in renewable energy sources around in ways such as the one we're talking about tonight, and to facilitate that investment and to support local community share ownership and to create opportunities for local businesses in the transition to a net zero community. We are a membership organization, so we really would encourage you all to become members. It's £10. And we look for volunteers as well with a wide range of skills. So if any of you have skills or interests that you could contribute to these efforts, please contact John afterwards, and we would very much encourage that and look forward to meeting with you in the future. Thank you.
Ready, Lars. Lars is a great friend of mine. He runs a company called Verderg, who have an innovative means of generating electricity from water hydropower scheme. So welcome, Lars. I hope they're letting you screen share so people can get rid of my face.
Yes, well, thank you very much. Yes, so you can also yourself. Let me get rid of that. Okay, so yeah, the company I work for is called Verderg Renewable Energy, and we've developed our own low-head hydropower technology. Tony asked me beforehand to give you a little bit of general information about hydro, even though he's just done that. So I'm just gonna skip through these 3 slides that I've prepared. But you know, he mentioned the Hoover Dam, which is essentially it's a hydro storage facility. So you build a big dam and create a reservoir, and whenever you need basically electricity, you open the gates and let water run through turbines. The other alternative, and that's a bit like Reading or Marlow or our project, which I'm going to introduce in a minute, is run-of-river. And run-of-river can be high-head. That means water drops from a big distance of 10, 20, 50, 100, 200 meters of height. It can also be low-head of 1.4 meters in Reading, and you have a way more like on the left side. So these are sort of the run-of-river and storage, and then low and high head and type of schemes. This is a pretty boring slide, but I just think it's good to get an idea of how much power we're talking about. So power is calculated by using the volume of water times the head. The head is the height the water would drop. And then you have rho and g, which are basically density of water and gravity. And you can just ignore the details and just say rho and g is a factor of 10. So essentially you calculate the power in water by taking the head in meters, the flow rate in cubic meters a second, which is 1 cubic meter a second is 1,000 liters a second. And you multiply it by 10. So let's say you have a 2-meter head with 5,000 liters a second. 2 times 5 times 10, that's 100 kilowatt. So in that water source that you have available, there's 100 kilowatt of power in there. But that's not the power that you get basically on your meter, because then you basically have to extract that power. And in order to extract it, you need to install a hydro scheme. So you might have channels where the water has to go through. So your head maybe drops from 2 meters to 1.8 meter. You need a turbine that needs to convert that power in the water into mechanical energy by basically spinning and that spinning then drives usually a generator. Sometimes you need a gearbox in between. Maybe need some bearings, some seals, and in the end you have a control system where the electricity comes together and it feeds into the grid. So all of these components, they have an efficiency. They all lose a little bit of power in the whole process of running through it, mainly in heat or in friction. And you end up with an overall efficiency. And that overall efficiency is usually labeled as water to wire efficiency. And depending on your system, it can be anywhere between a really, really, really efficient system, let's say 90%, or a less efficient system. But important is to not confuse turbine efficiency, which is just the turbine part, basically creating the power from the water into mechanical energy. Not comparing only the turbine efficiency to what's possible, because that's just sort of like, that's not comparing apples with apples. You need to understand what the entire system losses are. And efficiency is, everyone obviously wants to have a very high efficiency, but I will tell you in a minute that in our point of view, efficiency is only one part of the equation, because what really matters, and picking up on that question of what's the cost of energy, is the cost part. You can have an extremely efficient system, but if it costs the world, you won't build a project with it. And here are a few turbines that are basically been around, some of them around for ages. Left-hand side is more the higher head turbines. So Pelton and Turco turbines, what they essentially do, they feed water from a very high head through a pipe, which ends up in a nozzle and shoots a high, powerful jet of water onto a wheel, a little bit like a water wheel, but obviously very robust of steel, very, very specially designed shovels or pans, and then spins that wheel at an extremely high speed. So that's high head technologies. Crossflow and Francis turbines are sort of medium head technologies with high volume flow rates. So maybe we're looking 5-6 meter upwards, maybe up to 10. And then the Kaplan turbine is probably the most widely spread one, I would say, because it's pretty flexible. It can be used in high, low heads with smaller volumes or extremely big volumes. Is essentially like a ship's propeller in simple terms. It's like a propeller on a stick, but obviously it can be extremely high tech, where you can move your propeller blades, where you have guide vanes that are movable as well to change the angle, how the water hits the blades, and so on. And then on the right hand side we have the low head turbines. So there is something called the VLH turbine. It's huge, looks like an aeroplane engine almost. But even that is not truly low head. So because it's such a massive beast, they sort of look at projects from maybe 5 meters upwards. On the top right, you have the screws that Tony is using. Basically, water falls into an Archimedes screw, which used to be in the ancient times to basically pump water upwards. In this case, it's flowing into the top of the screw, and gravity basically makes it turn whilst it's toppling down each flight and spins the screw. A vortex turbine is essentially a huge circular basin where the water flows in with a drain plug in the bottom, and the water starts spinning like in your sink or in your toilet, and it spins, and there's basically a propeller turbine vertically in the hole in the bottom of that circular tank, and basically drives a generator. And on the bottom right we have our technology, and I jump straight in to that technology. Unless, how do we deal about questions? Shall we do them at the end, or?
Yes.
Yeah, okay, let's do them at the end. All right, so why have we developed a different type of hydropower turbine for low head? Now, the challenge with low head is not so much about getting the power out. You know, hydropower has been around for centuries, and there's obviously plenty of systems out there that can produce power out of low head hydro settings. The problem is the cost side of things, because as I explained at the beginning, the power that you get, and power equals money, quite frankly, is driven by the head. And in low head, and we're talking anything, let's say lower than 4 meters, you know, the power is smaller because your head is smaller. So you need to find something which is actually very, very cost efficient as well. Not only energy efficient, but also cost efficient. And there are certain restrictions that are driven by physics. And that basically means with low pressure and head, water height, head is pressure, your conventional turbine ends up very big, like we've seen on the images, rotates very slow. You need a gearbox, and every equipment that is huge is expensive, not only to manufacture, but also to install and to maintain. So we have developed what we call the Venturi enhanced turbine technology. So essentially what we're doing is we're splitting the flow up into 2 parts. So we're basically sending one part of the water just through a venturi, and the venturi is essentially a pipe which narrows down. So the water that flows into that large pipe, because the diameter of the pipe goes down, the water is speeding up. And when the water is speeding up, it creates an area of low pressure. And then we're taking the remaining part of the flow and sending it through a normal propeller turbine, the ones I just showed as well, but obviously of a much smaller scale. And that propeller turbine discharges into that extra area of low pressure that we've created. So by doing that, the turbine, this turbine, which discharges into that extra low pressure, does not see 3 meters of head across it that you maybe have on the side. It now sees over 7 meters of head. And by increasing the head, you run the turbine up to 15 times faster, and the whole turbine becomes up to 5 times smaller. And that's essentially what's driving the costs of low head hydropower down. So I'm going to talk you through now the project that we have installed, and the very first one that we have installed in Eton-Soken and Cambridgeshire. And essentially the setup of the project is a bit like this. So you see the device here on the bottom right. And essentially we've built a tank where the water drops in, and then we've splitting the flow up into 2 parts. So the main part just goes basically through the pipe, creates the low pressure area in that venturi. And the remaining part goes through a small fish screen and into the turbine. And we have an underwater generator, which then produces the electricity. So now I'm literally running through probably a dozen photos or images just to give you an idea of how the system looks. So this is an old mill, the river mill in Eton-Soken. There is a weir basically in the top right corner, so the river runs from right to left. And this mill used to have hydropower turbines in it installed in tunnels that are run under the mill. And we've opened up one of these tunnels and basically installed our system down there in one of these culverts. And it's a grade 2 listed mill. So it was a very difficult project because the whole system is built literally 50 centimeters right next to that mill. And yeah, we had to be extremely careful when we were doing this. So here you can see, this is the old culvert, or one of there are 3 culverts, but we're only using 1. And at the entrance of that culvert, which is here, so this is a marina, which is the upstream bit on the top left. And behind this wall sits this tunnel or this culvert, And we've basically installed a debris screen, which is essentially like a filter, you know, large pieces of debris that comes floating down the river and would basically try to get into your turbine tank. It gets stopped there, and that also needs to be regularly cleaned to not block it essentially. So we had to build a small cofferdam on this end to build an intake structure, which with the debris screen. Then we have on the other side, we have this is the downstream side now on the bottom right, which is like a mill pond, and this is our venturi pipe, which is out of GRP plastic essentially. It's on a frame, and there are piles basically driven into the mill pond, and the pipe essentially is hung from the top into the water. So it's not sitting on a foundation. It's just supported from above and lifted into the ground. So one problem we had, and funny that Tony mentioned it at the beginning with cofferdams flooding. The original plan was actually, as you can see, this pipe is in several sections. I think it's 5 or so sections, which are just flanged or bolted together. The idea was originally to basically lift each section on its own in there and bolted on in the cofferdam, which was supposed to be pumped out of water and that. But equally to his project, we also had the cofferdam flooding. So they literally decided, you know what, before we try to get this cofferdam dry again, we're just going to assemble it outside and lift it in one piece. This is the turbine. So this is this project takes 4,000 liters a second, but the turbine only is 40 centimeters in diameter, and it's a normal propeller turbine. It doesn't have movable blades or guide vanes. It's a very, very simple turbine, and it's a bulb turbine style, which basically means the turbine sits here in the turbine casing, and a drive shaft connects directly to a generator, which is in this small tube section. So the water goes from right to left. It goes basically around the bulb turbine and goes through the turbine, spins the blades, which drives the generator, which produces electricity, which comes out through these cables. And the whole system is mounted on a skid, so we basically just lifted it in. And I show you, yeah, that's the inside. So in the inside, basically below the decking you just saw, there is this rectangular tank that I showed you the schematics of at the beginning. And here you can see that fish screen, which basically sits on these frames. And the water is literally coming into the picture. Some of it basically drops through the fish screen and goes into the turbine, but the majority of the water goes over the fish screen, keeps it clean, so we haven't had to clean that fish screen once, over the fish screen and basically into the main pipe down here, and creates the low pressure area. You can see that long tube now, which is connected to the turbine, it basically sticks into that low pressure area at the bottom. So this is how the river mill, maybe I forgot to mention, it's a pub. What a pleasure to work at a pub. It was looking before we came and did the system, and that's how it's looking now. So you don't actually see much of a difference. We've tidied it up a bit, but essentially under this decking is the entire structure. So under this area here is a 4 meter deep tank. And the only thing that is sort of above ground is this green kiosk here, which houses the control equipment. That's the inside of the green kiosk, and there is another cabinet in there with a display where you can control the hydro from, but you can also control it remotely, even from your mobile phone. And yeah, this is sort of like an added terrace that basically sits on top of the tank. It's very useful for the pub uses. It's a beautiful spot looking down into the mill pond, and this is the structure on top of the pipes, which basically is hanging under there, and we've basically put a decking onto it as well, and eventually it could be used for seating, for sitting, a seating area as well. And at the very end of the pipe is a sluice gate, which literally goes up and down, and it controls the flow through the whole system. So it sits at the end of the pipe, and it controls the flow. In another project, we might move that to the other end, to the front end, but yeah, it depends on the site. This is the mill before, so this is the marina, and now this is the intake with the debris screen once it was installed. So the technology is scalable. At the moment, obviously, it's a 25 kilowatt scheme, but our big intention is, to scale the technology up and to eventually, address tidal projects, of several megawatts, several hundred megawatts, and we've been through the development process of that, and that's sort of long-term aspirations for us to eventually sort of create, build a prototype for a bidirectional VET, which can then be used in tidal estuaries and generate vast amounts of electricity. But that's the long-term aspirations. Right now we're in that process of bringing the river technology to the market. Okay, let's do some questions.
Yep, lovely. Thank you, Lars. I'm not sure who's got the questions. I think if you'd like to ask a question, then you can either put it in the chat and we will look at it, or put your hand up. We've got Andrew's putting his hand up, so we'll go for Andrew's question first, I think, please. Okay,
very interesting, Lars. You say the venturi effect increases the effective head going into the turbine. I think you mentioned a 4 meter head becomes effectively a 7 meter head, but presumably to gain the venturi effect, you actually you're losing flow water. Most of the flow goes through the venturi, not through the turbine. So you may gain head, but you lose flow.
Yes. Yeah. No. Yeah. You're absolutely right. So the big portion of the water that's going through the venturi to create the low pressure. Obviously, there's no turbine sitting in that, so you're only extracting the power out of the smaller flow with the higher head.
Okay. Yeah. I got another question about the Eaton Socken installation. Is surplus energy fed into the grid or sold to the grid at all?
Yeah, exactly. So it first powers the river mill, and every excess is going into the grid.
Okay, and presumably, likewise, if the river dries up, or the stream dries up, then they can seamlessly change over to the grid.
Yeah, exactly. It's happening completely automatically.
Okay. Okay. It looked very interesting and most professionally done. I must admit, it looked very good.
Yeah.
Thank you.
Thank you, Lars. Is there any more questions? Yes, we do. Liz, go for it.
Okay. Hi there, Lars. That sounds really interesting. Have you actually been to Marlow to see the situation of the river in Marlow?
No, I haven't actually. So I came into this call very unprepared.
Okay.
So I would actually be very interested to hear what your hydro plans are.
Yeah, well, I don't know whether anyone has, dovetailed Lars's ideas with the actual situation in Marlow, because originally there was a hydro scheme that was planned on the weir. The weir is in a very sensitive, visually sensitive site, because it's right in the center of Marlow, and if anyone ever takes a photo of Marlow, it's there in the weir, so it's a very sensitive area. However, we do also, and I don't know anyone who really knows, anyone here really knows about the river flow underneath, I think it's called the mill houses. You know, the white, we've got about 4 or 5 white houses that are to the left. And I believe they have like a flow underneath them. So, you know, I don't know whether anyone's actually sort of looked at that. I've always felt that that's actually the less sensitive visually possible site, and also looks, interestingly, a little bit more like your scenario in Cambridge. So I don't know whether anyone is aware of the actual physical flow at that point, or whether you'd even thought about whether this is something that would be done on the weir or hidden away underneath these houses.
Yeah.
Or maybe you just don't know because you haven't been here.
Yeah, no, I don't know, but I mean, the only thing I would say is it can be, there are many ways of installing it, and you basically have to look at each project individually and see what works best.
Like, I think that for me, the nice thing about Marlow Weir is if it had Veit turbines in it, you wouldn't see anything, maybe just the control box, which doesn't necessarily even have to be that visible. That could be some distance away, and it would be not really very big or obtrusive. So you maybe have some extra sluice gates or something like that, but the whole thing's underwater. It would be a bit tricky building it because you'd have a major building site going on near the hotel and in the middle of the river, but that's a limited period of time. So I think under the mill houses, there would probably be problems with paying them off or leasing their land or leasing their water. And there's probably all sorts of kind of complexities involved with that, which in my view wouldn't even warrant getting started with it. But anyway, yeah, thank you, Lars. Any more questions, guys?
Thank you.
Yeah, there's a question on the chat, sorry, about cost, and I was going to ask about cost
please.
as well. Do you want to do the one on the chat first, because that was there before me?
Yeah, I'm not very good at doing it, but I will try. Yeah, here we go. In the trade-off of flow for head and the smaller size and capital cost, roughly, what is the pounds per kilowatt installed, please, Lars? Yeah. I'll manage to duck that question myself. Good luck.
Well, we can give it to you in a minute. So first of all, I mean, it really depends on the size. So we've been looking at projects. I mean, we know our project, which is around 25 kilowatts, and we've been looking at projects of 100 kilowatts, 150 kilowatts. And I think the range we're looking at is between, let's say, 1,500 pounds to 2,000 pounds per kilowatt installed. But it is extreme, and that's the equipment side of things. You know, you obviously need to look at civil works, planning, design, and so on, and that extremely varies between projects. Yeah,
thank you, Lars. Do you want to go for yours then, Mike?
Yes. It was just to compare it with the Archimedes screw. So is your solution cheaper? And I really enjoyed the presentation, Lars. But is it cheaper than an Archimedes screw approach? Or the same, or
in our view, it is, or it will be. You know, we've now built the very first one, so we definitely have potential to improve. I don't know if Tony can share his equipment costs with the screw per kilowatt.
I think we're probably just over 2,000.
Yeah. So yeah, it is, and then obviously there is this element of the civil works or as well. So it can that can obviously swing the decision, whether one technology is superior over the other. Yeah. But I think once we've gone up to scale, once we've done a few, I'm pretty sure we can drive these costs further down.
Yeah. I think the fact it's pretty invisible is a big plus, probably, in terms of getting it agreed. But yeah,
I think the other good thing about it is that it doesn't change the flow of the river, and it actually could offer better control of the river flow, because the venturi sits there, and if you switch off the generator, it lets more water go through because it's not extracting energy. And so the Environment Agency should really love it, and they would get effectively free control or overhaul new weir gates for anything that went in.
Yeah,
So
you essentially increase the capacity over the weir. So
Yeah.
if flooding is an issue, it basically allows you to let more water through from upstream to downstream if you want to. Otherwise, you obviously close the sluice gates, and you're back to where you were.
So, I mean, sorry, obviously talking about Marlow weir, do you ever consider Hurley weir and Hambledon weir at all? Because obviously that they also do not have any power generation on them.
Yeah. No, I haven't.
Yeah.
I must admit we're not perfectly up to speed with opportunities currently in the UK. Since the feed-in tariff is gone, it is so extremely challenging to do projects economically in the UK.
Yeah.
And even, I mean, I would say even us with what we think is a more cost-effective technology, I struggle to do projects. So we've been looking a lot internationally. We're spending a lot of time at the moment, basically setting up partnerships in Brazil. So it's a shame, and we're not ignoring. So every opportunity, and for example, the Marlow one, if there is a true interest, I'm more than happy, to do a trip and have a look, and we can do an energy assessment pretty simply to see what kind of power can be generated. So we're definitely not ignoring UK projects, but we know it's extremely challenging at the moment to get them actually off the ground.
Yeah.
George has a question.
Oh yeah, we got one. George, go for it.
Well, it's probably more for Tony, I guess. I mean, I did follow the original idea to put a turbine in the Marlow weir a while back now, 10 years ago, I suppose it is. And one of the issues was that the Environment Agency wouldn't let you extract the full energy flow of the river. I mean, if you do a back of a fag packet calculation, you've got about 0.5 megawatt, I suppose, average. So, but they only let you extract 20%, as I remember it. So it's down to 100 kilowatts.
Yeah.
Is that the same problem that you? I mean, it's not a problem necessarily, but is that an issue you still got in Reading now?
We only extract about 10% of the flow in Reading, so even less than your 20%. It does. You have to look at the economics quite carefully. Like, we could install 4 turbines, but the 4th one would be only less than 50% effective in it, because it would not be generating all the time. So it costs twice as much. So 2 is fine for us. If it was Venturi, we'd probably have 4. But because Venturi doesn't interrupt the flow of the river, there's quite a strong case for saying that you could stick it on all the weir gates in Marlow. And if they want it to go into spate mode, then you just turn off the generators and water goes through quicker. But it's really, I think the Environment Agency are going to have to change in the future, and whether that point is yet or not, I don't know. But I think there's a very strong case for Marlow doing some. So you've got Andrew coming back with another question. Go for it, Andrew.
Just supplement to that question. Lars, what is the approximate proportion of water that flows through the venturi to water that flows through the turbine?
So, I mean, we can change that depending of how high we want to amplify the head, but it's in the region between 20 and 30%.
20 to 30% goes through the turbine.
Yes.
Yes. Okay, and 70% goes through the vento. So in terms of Marlow weir, if the Environment Agency is insisting on what was it, 20% only extracted for power, you still got you could use the Venturi ones and get effectively more than 20% out by the Venturi effect, by increasing the head through the Venturi effect, while still allowing the the uninterrupted flow through the venturi.
Yeah. In theory, yes, I think, and in reality, unfortunately, I think the EA treats every drop of water that basically goes through a system, whether it actually goes through a turbine or just through a pipe, as water being abstracted, you know. So, but I mean, I think the 20%, you always need to look at it also in a relation to the flow duration of the year. You know, you have over the winter periods or spring, autumn periods, extreme volume of water coming down the river, and then you have air times in the summer where it's a lot less. You need to find the right sort of design flow essentially to scale the system. And you got to accept that, you know, you won't be able to cover the high flow periods with your system, because if you would design your system for the top end of the flow range, it means a lot of the time of the year you don't have actually enough water, or you run it in on partial mode, which is very inefficient. So you got to pick somewhere in between. So, and it's usually around the average flow anyway, maybe even a bit lower, just in order to keep what's called the load factor. It's basically the time, the hours of the year the system is running, you know. Reading, because Reading was given these sort of restrictions of how much water they can take, and it's sort of a bit of a smaller amount, it actually means that they have a fairly high load factor. It means, I think that, I don't know exactly what the calculations were, but we looked at the project in Reading as well, Tony, but we were a little bit too early in our development stage with the technology. But you might have like a 70-75% load factor, which means throughout the year the system is running 75%. That's very high. It's usually more like 40 to 50.
Yeah, okay, lovely. Thanks very much. I think I'll let John have a question now.
Yes, thanks, Lars.
Yeah, I think it's more a bit of information than anything else. I go past Temple Lock from time to time, and there's obviously a weir there as well. But right next to the lock itself is an old flash lock, which has a nice little slope on it and would be hopefully an ideal place to put one of these turbines.
Yeah, thank you.
I mean, I will, I don't know who's the best one to contact, but I will come back to one of you and collect the list of all these locations and do a road trip.
I think the Environment Agency have identified the weirs on the River Thames which are suitable for hydro, so you should better pick up that list somewhere. And I don't think it includes Marlow, but that's because the Environment Agency did the list. So there's a list of them, ones that would probably be viable and economic. So have we got any more questions? Oh yeah, we have. Yeah. Is that Liz again?
It is Liz again, yes. Yeah, just because again, I was sort of around when we were looking at the hydro scheme initially.
Yeah.
And one of the problems seems to be you need somewhere to use the energy, and preferably somewhere quite close. So I think possibly your Temple End, the Temple End one is probably not good because it doesn't have place to use it. It's not got a big population very close to it. Your Marlow is quite good like that. They looked at combining it with the Complete Angler, which is a large hotel right next to it.
Yeah.
Or potentially the island. There's an island in the middle of the river that they could use it collectively as there's a group of houses. And I know that Maidenhead also looks. So if you do come here, you know, obviously you want to have a look at a number of them to see which is best and what's suitable. But Maidenhead, they tried to get use their weir, their lock. I think what's that lock?
Bolter's Lock. Bolter's Lock.
Yeah, Bolter's Lock. I think that was a possibility again because they've got a big population base that's very close by. So that would be the one to look at, and they're all, you know, you can drive from one to the other.
Like, I think the way things are changing, the Complete Angler should be mega keen for green electricity. Like, it would give them so many brownie points points and raise the profile of their hotel if they had hydroelectric power effectively powering the hotel, because their use would be higher than Marlow generation, in my opinion.
Exactly. You just need to make sure the fishes are protected. Make sure you
Well, the
talk
fishes
about the
are
fish screen first.
Yeah. Yeah, I mean, they just get washed straight through. Lars is
Yeah.
really good.
They might like that.
Yeah.
Yeah, we've done 2 trials with hundreds of fish that we had to do before we got our accreditation from the Environment Agency. So yeah, they're all happy.
Can I just mention on Temple that actually there are about 100 houses by Temple Lock, 60 on the island and another 40 or so in the village itself. But our fall, of course, is only about 1.3, something like that. So it's not very great.
I've got a feeling that Temple might be below the minimum. I think Lars has got a better chance of doing it with Venturi, but even below 1.3 is going to be starting to get difficult.
Yeah.
But selling it to private consumers becomes very interesting. And I think the whole electricity market's going to change in the next few years to make that sort of arrangement much more allowable.
Yeah. Yeah, I mean, it is the power offtake is, again, since feed-in tariffs are gone, another area which needs solving. You know, you generate the power, but where do you put it? And if you don't have a single large consumer, you know, you can't run cables to each and every household. So you need to somehow tap into the grid. And there is talks, and I'm not up to speed with it, even though I should be, but about like community grids and things like that, where ideas are around, but I'm not sure it's solved yet. And
I've just dropped a link in the chat. There's a campaign about doing exactly what you suggest, called the local electricity bill. It's about, you know, trying to reform the electricity market. It's just impossible at the moment from a regulatory point of view for a community energy scheme to sell power to 150 houses. It's not allowed.
Can I just say, guys, I need to depart now, but thank you very much. It's obviously much too early for us at Temple, and maybe in the future, when these systems develop and get even more sophisticated, there might be a future for us. But it has been very interesting, and we'd like to sort of keep tabs on what happens in the future. So thank you for inviting me.
Yeah, thank you.
Thanks.
So I would just say, coming back to Hurley, thinking about it, of course, you've got Danesfield Hotel there. So just like the complete Angler scenario, you've got another big power consumer kind of just up a hill from the weir. So another one to put on the list, I would think.
Before we disappear, can I just promote 2 events?
Yes, sure.
I'll share screen so you can see it. Basically, let's get that one. Hopefully everybody can see that. This is our next event. It's not an Ask the Experts one, it's a special one from Marlow Bridge Rotary Club, who are very supportive of Marlow Energy Group and are helping them at the moment put a video together. So they'd like to tell us more about their organisation, and on the 6th of April they will do that. There's a link there. This will also be on our website, so you can access it from there as well. In addition to that, in May, and we haven't got a date yet, but in May we have an Ask the Experts, so back to Ask the Experts on plastics, and we have 2 speakers there. And that hopefully will prove to be an extremely interesting and informative talk. So look on our website for either or both of these events, and we'll be delighted to see you on either night or both, as the case may be. Thank you, Tony.
Yeah, thanks. And thanks, Marlow Energy Group, for letting us bring Lars here and talk to you about hydro. I really enjoyed it. I think we say clap for Lars. You can probably have to do clapping with the special one. If you don't know where it is, it's in there. There you go. Yeah, thanks very much, everybody, for coming. I've really enjoyed listening to Lars again, and I hope your business goes more and more successfully. I'm sorry that you're doing it abroad more than in the UK, but there will be opportunities here in the future. Thank you, Lars.
Thank you very much, everyone. Bye-bye.
Okay, bye-bye.
Bye-bye.
Thank you. Bye.